Child. Okay. Now, we are going to discuss certain theoretical, ideas and concepts behind duality that allow us to, in a way, that allow us to use the results. See, in the last class, we just learned how to read the solution of dual from the optimal table of the primal, and how to read the solution of the primal from the optimal table of the dual. Okay, but then the point is that we should have a theoretical proof behind it. I mean, we should be certain, we should be sure about why. If we are doing it, then why we are doing it. Okay, so for that we have certain results, and we have around basically 3 to 4 important results on duality, but we won't be proving all the 4. What I'll be doing is just discussing 2 major results that can be asked theoretically also in the exam. So I'll be proving only those 2, but the remaining, the main important result I'll be discussing without the proof. Okay. See, the very first theorem that we do on duality is the fact that the dual of the dual is primal. Okay. Now, this, as I explained, just randomly in one of my earlier class, because we are using the concept of matrices. In fact, the idea comes from here only, because your coefficient matrix is this matrix A. Okay, so what we do is that we use this concept of this transpose of a matrix while writing the dual. And for matrices, we have a standard result that the transpose of transpose is the matrix itself. So that idea, that concept gave us the idea for this result that we are going to prove here. And as you can see, the statement of this theorem says that the dual of the dual is primal. So what basically we do is we start with a linear programming problem. So as you can say, I have taken a maximization and less than or equal to type problem, where all the right hand sides are positive. Of course, no, not the positive. It's not the standard form. It's a canonical form that I have written, that it's a maximization less than or equal to type problem. So I'm assuming that my problem has n number of variables and m number of constraints. So that's why this matrix A, which is the coefficient matrix, is of the order m cross n. Okay, and the matrix B is of the order m cross 1, because the right hand side is going to have m number of rows here. Okay, so these are my right hand sides, B1, B2, Bns. These are the coefficients in the matrix A, and that means the coefficients in your set of constraints. Your matrix C is this matrix of coefficients of the objective function. Okay, and your matrix X is your matrix of the variables x1, x2, xn. Now, because I wanted this product to be meaningful when I'm writing Cx, so that is why though I have taken X as n cross 1 and C as n cross 1 also, so but when we write, it is obviously the matrix is meaningful. Okay, similarly AX, the matrix is meaningful, right? And the dual of this problem is going to be something like this. Okay, I have taken it as now ZY. The primal was ZX. I have taken it as ZY. So obviously your right hand side of the primal becomes the coefficients in the matrix. So your column matrix becomes a row matrix, right? And you have a new matrix Y, and subject to, of course, we take the transpose of A, and this becomes more than or equal to C. So this is how the dual would be written in matrix form, right? Now, I have to prove that the dual of dual is primal. So what I have done is I have taken the dual of this matrix, this problem again. And instead of calling it back as X, I have introduced a new variable W here. Okay, so for ZY, that means now this problem becomes my primal, So I'm writing the dual now. So minimization problems dual will be maximization. So instead of zy, I have written zw, and the same logic has been followed. That was followed while writing the dual. Okay. So I have this now. Okay. So C transpose W. So A transpose W will be less than or equal to B transpose, where I have introduced a new set of variables W. Okay. Now, where W is more than or equal to 0. Now you use the basic results of matrices. So C transpose is C. So you get back this problem, okay, which is similar to your first problem, except that instead of X, you have a W. So if I replace W by X, I'm getting my same problem back. Okay. So this proves the fact that the dual of dual is primal. Okay. Now, this result has been asked, so can be asked again. It's too trivial and too logical and too simple. Okay. Now come to this important result, because this is an interesting result, because this is actually, this is going to form the basis of the fact that, we are going to use this result and use it to have the main result, which allows us to read the solutions of primal from dual and of dual from primal. Okay. Now, what does this say? See, it says that if X is a feasible solution of the primal problem, again, primal problem maximization less than or equal to types, and Y is a feasible solution of its dual. So obviously the dual is going to be the minimization more than or equal to types. Then, see, look at this result, what it says. It says that Cx is always less than or equal to B transpose Y. Now, Cx means what? Cx means the objective, the value of the objective function of the primal. Okay. And B transpose Y means the value of the objective function of the dual. Right. Now, this result proves that the objective function value of the primal will always be less than or equal to the objective value function of the dual. Okay. Now, this is what I was trying to explain the other day. And that's why we call this as the weak duality theorem, because this does not say equality exactly, right? This just shows the relationship between the values of the objective functions, okay, for two different problems, which are related to each other, in the sense that one is the dual of the other. Okay. Now, see, what happens is geometrically, if you see, I'll have to shift just a minute. I'll try to share my, I'll try to switch on to another file, and I'll try to explain this geometrically. See, what happens is that you have both the solutions of both the problems also that we solved, the primal and the dual, right, with you. See, what happens is geometrically, if you try to see, supposing I have a function, a linear programming problem in two variables, and we geometrically plot, supposing this is randomly I'm doing, supposing this is one constraint. I'm just trying to explain. Say this is another constraint, and supposing I have this, right? There's two constraints I've taken and two variables. So basically, this is your feasible region, okay? And you will observe that this kind of a feasible region normally comes when mostly you have maximization problem and less than or equal to type constraint. So this becomes your feasible region. Now, what happens is that when we solve the maximization problem algebraically, if you look at the simplex method, you will observe that the first simplex table always gives you the value 0, z as 0. And what happens that if you have a maximization less than or equal to type problem, Your initial, when we talk of the initial basic variables, they are always your slack variables, because that is how we still solve. If you can possibly just go through those pages where you have solved the problem that I gave you, 90, 60, 80 wala. You have the solution of the primal with you, you have the solution of the dual also with you. So if you just open both the simplex tables in front of you, you will see that for the primal, the first simplex table, if you just forget about the other, I'm not talking of the optimal table, I'm just talking of the first simplex table that you have. So if you were to read the solution from the first simplex table, what will you read? The values of x4, x5, x6 as 90, 60, 80, right? Maximum z, 0. But what about your decision variables, which were x1, x2, x3? That will be read as 0. Okay, so that means your solution is what? 0, 0, 0, right? So if you plot it in a three-dimensional, xyz coordinate plane, what will be the solution? The origin, right? Similarly, if you just have two variable problem, that means this is the first solution that you get. So basically what we do is, when we are solving a maximization problem, we start from the origin, okay? And then gradually we move on. So even if you plot the z, the straight line for the objective function, your first objective function will be this, something like this. This is your line z equal to 0. So what we do gradually when we are solving graphically, we increase z in this direction. Okay, so as you give different value to z, you get this line, and so on. You keep on moving till you reach this point. Okay, so this becomes your z, which is going to give you the maximum z, and this point, whatever be the coordinates, that becomes your optimal solution. Okay, so this point A will give you x1 something and x2 something. Okay, so basically what is happening is that we are moving from origin to some positive value of z in this direction. That is when you're solving the primal, right? Now what happens when you solve the dual? So when you're solving the dual, you're solving a minimization problem, and it is going to have some basic solution, some optimal solution also. So definitely your feasible region obviously will not be this, okay, because your constraints have changed, right? So what will happen is your feasible region will be, let me try to build the your feasible region will be somewhere, it could be anything. So I say somewhere, something like this. Supposing this is your feasible region for the dual. Okay, so what happens is that because now your dual is a minimization problem, right? So if you just open the first simplex table of the dual, right? Now, if you solved it by big M method, the first solution would have been in terms of minus m, right? Where m is very large, okay? So what would happen in that case? That means your objective value function is somewhere up here, something very, very large, but in terms of infinity, right? So somewhere up here that you are starting from. If you solved from two-phase method, then you can directly come down to the first table of the second phase. Okay, it would have given you some value, right? But that would be something like very high value of z, say. Let me check. It must have been somewhere around, was it 970 by 5, something like that. So almost 190 something. Okay, so that means somewhere here. So what is happening is that you have your z here in the case of a minimization problem, and you have your z here in the case of maximization problem. So that means the primal moves from here to here, and the dual moves from here to here. Okay, but definitely at any stage, the objective value from the primal is here, and objective value for the dual is here. So definitely this is always less than or equal to this. This is what weak duality theorem says. That at every, if you compare the simplex tables for both the problems, at every table you will find that the objective value of the primal, that means this value, is less than or equal to this value. That will always happen. But what is happening? It is moving from here to here, and it is moving from here to here, and they are meeting at some point, right? So that is your optimal. So that is what the strong duality theorem says. It says that if the primal has a solution, optimal basic feasible solution, X star, and dual also has a optimal basic feasible solution, then those two optimal basic feasible solutions are equal. That is called as the strong duality theorem. Okay, but weak duality theorem says that the optimal solution for primal is not the optimal. The objective value function of the primal is always going to be less than or equal to the objective value function of the dual. Okay, and that is happening. Now, don't mix with the negative, because the dual is a minimization problem. So algebraically, when we solve a minimization problem, we convert to maximization type. Okay, so definitely whatever objective function you are getting in your solution, that is the minus of it, because we convert it to maximization and then solve. But actually, the value of the objective function is minus of what you are getting in your simplex tables. So, which is the plus value only. So, at one stage of primal, if your value was, somewhere around, you must have seen it, 180, then for the dual, the corresponding is 195. So that the optimal is obtained at 190 for both of them. Okay, that was the objective. That was the optimal solution for both. Okay, so this is the logic behind the two major important theorems. But for you people don't have to prove the strong duality theorem. Some books, some authors also call it as the duality theorem. But to give a distinction, we call one as weak duality, the other as strong duality theorem. Okay, so since we won't be proving the strong, we just need to prove the weak duality theorem. The proof is very logical, and I'll come back to the proof again now, so that we can just quickly understand the proof, because now I've explained the logic, so probably now understanding the proof mathematically won't be too tough for you. Okay. So what we are doing is, we have started with this maximization problem and with dual. So what I have done is, I've just taken up any feasible. If you are confused, you can take it to be X dash or X star, but it's understood that I have started with any feasible solution of the primal as X and Y as any feasible solution of the dual. Now, because they are feasible solutions, so definitely both of them satisfy their constraint sets. So we are getting AX less than or equal to, both the constraints are satisfied by this, like AX less than or equal to B and the ATY. So I've numbered this equation as 1 and the second set of constraints as 2. Okay. Now, when you move on, what I have done is that multiplied the first equation by Y transpose, both the sides. Okay. So what you get is this. Okay. And Y transpose B, I can write as B transpose Y, because I've just reversed the order. That doesn't make any difference. And multiply the second equation by X transpose, pre-multiplied by X transpose. Okay, but did not change the second equation because I wanted. Wait just a minute, my mouse is. Okay. Let me see. Okay, so now what you do is, in the second equation, take transpose on both the sides, use matrix properties of transpose, and you get this. Okay, so now what do you get? That Cx is less than or equal to this, which from this equation is less than or equal to this, so which proves the fact. So that's what I said, it's very logical. So no, nothing greatness in the mathematical proof, but it's very logical. So you get that it's always going to happen that your objective value function of the primal is always going to be less than or equal to the objective function value of the dual at every stage. Okay, and this is what I was talking about. That this is the strong duality theorem, or the duality theorem, which says that if either the primal or the dual has a finite optimal solution, then the other one also possesses the same, and the optimal values of the objective functions of the two problems are equal. So that is where, both of them are going to meet each other. Okay, so this is what strong duality theorem talks of. So it is this strong duality theorem which ensured that we can read the solutions of one from the other. So we need to solve only one problem. And why the biggest advantage of these results is that, as again I'll mention, that if you have more number of variables and less number of constraints, your number of iterations are reduced. Okay, so we preferably tend to solve those problems that have less number of constraints. So if I'm given a problem that has more number of constraints, I can always write its dual, convert it to a problem that has more number of variables but less number of constraints, and solve it, because it will take less effort and less time. So once I've solved the other problem, I can always interpret the solution, of one from the other. So it's not going to create much of problems to me. So that was the major breakthrough, in this, and it is, and in fact, this concept of duality was exploited most by economists, because reading the constraints and interpreting the slack and the surplus variables, that is why we have an economic interpretation attached to them, because they tell us about, see, why I'm saying economics, because practically if you look at these problems, they are dealing with resources and outputs. So basically resources also have money or cost involved with them, and outputs also have money involved with them, because we are talking of revenues in that case. So definitely everywhere money is involved. So definitely when we are talking of solutions, when we are talking of outputs, then somewhere down the line economics is involved. So definitely we talk of economic interpretations for that. So for that, uh, if you come back to the problems that we have solved, I'll be now needing the optimal table of primal solution that we talked of the other day. The very first problem that I gave you, that carpenter wala issue. We'll come to that. Okay, and then I'll just need the optimal table for that. Do you have it with you? Hmm? Okay. I'll just write the optimal table. Primal ka, okay? We had how many variables? X1, X2, X3 were the decision variables. X4, X5, X6 were the slack variables, right? What was the coefficients of the primal? 3, 4, 1, 0, 0. है ना? यही थे ना? Just correct me if I'm wrong. The basic variables in this order were X2, X1 and X4. No, X6, sorry.
X6.
Right? So they were 4, 3, 0. The right hand sides were 40, 10, 10. Right? Beach value values we can do away. Don't need them. I just need the, yeah, your Z was 190. ये आया था. And yours, I just need ZJ minus CJs. So they were 0, 0. X3 का कितना था? 14 by
3.
14 by 3. X4
5 by 3.
5 by 3. X5
2 by 3, 0.
2 by 3 and 0. यही था ना हमारा optimal solution. I don't need the middle value, so I'm not writing because I just need an explanation here. Okay, now let's come to the three constraints that we had. The constraint number 1 was with regard to the wood, right? The constraint number 2 was with regard to what did I say? Machine time. And the constraint number 3 was with regard to the special kind of polish being used, right? Now, in this case, our X1 were the number of units for, what did I call them? Chair or table? What was that? Something? Do you remember? I have forgotten. Okay, let's call it chair. X1 was chair, X2 was table, and X3 was bookshelves. Am I right?
Yes.
Yeah.
Yes, ma'am.
Right. So these were the three things. I mean, physically. I'm coming back to physically because we are going to interpret it physically. Okay. Now, if you read the solution and you have to tell the decision maker, you know, what all he should do to earn a maximum profit of 190 units, right? If the market continues in this manner. So what are you going to tell him? You are going to say that X1 is how much? 40. X2 is 10 and X3 is 0. So this is the solution. Your physical decision variables were only these three. And while solving, we have got X3 to be 0. And if I look at the other solutions that I have got, I'm getting X4 0, X5 0, and because X6 is the basic variable, I have got X6 as 10, right? Now this has turned out to be a positive value. Now, that means basically you are telling the decision maker that he should go on manufacturing 40 units of chairs, 10 units of table, and no bookshelf. Okay? And this kind of an arrangement is going to earn him a profit of 190 rupees. This is what we are going to interpret from here. But then, you know, if you just look at it, just says, I mean, how come he doesn't make any bookshelf? And why is it so happening, right? Ideally, if things were if things were being used, being consumed in an ideal manner, then technically and logically also, he should be producing all three. You know, why only two to earn a revenue? Okay. Now, when you look more closely into your solution, you are getting that one of the basic variable is still one of your slack variable. Okay. Otherwise, if things are ideal, then all your physical decision variables should have been optimal basic variables. So that we end up saying, okay, x1, x2, x3, itne chair, itne table, or itne bookshelves, and this will earn you a profit of these many rupees. That is a perfect situation. Okay, but then we have not reached perfection here. So something needs to be seen more closely in such situations. Okay. Now, what we observe here is that x6, x6, which is here as one of the basic variable, has a value 10, right? Now, x6 basically was introduced as a slack variable in my third constraint. यही था ना? X4 was a slack variable in my first constraint, X5 in the second constraint, and X6 in the third constraint. Now, what was the third constraint? The third constraint was actually 3x1 plus x2 plus 2x3 less than or equal to 80. यही था ना? Which was the corresponding constraint for the polish being used. Okay. Now, what you have got, what we did was actually we changed this inequality into equality by adding x6 to it. Okay. Now, if I'm saying x4 is 0 or if I'm saying x5 is 0, basically what I'm trying to say is that, see, x4 was added in the first constraint to convert that inequality into equality. X5 was added in the second constraint to convert that inequality into equality, and we have got their values to be 0. So that means if I just look at the first and the second constraint, then the utilization is equal to the availability. Why? See, because x4, yes, or even x6, this x6 actually denotes the slackness in your utilization in comparison to the availability of the resources that we have with us. Okay, so if they turn out to be 0, that means for that particular resource there is no slackness. That means it is being utilized optimally. There is no lacking in the utilization of that resource. So as far as the wood is concerned, as far as the machine time is concerned, we are utilizing it optimally. Okay, but when it comes to x6, we are getting the solution as x6 equal to 10. So it is not 0. Okay, that means some amount is lacking in the third constraint. Okay, so this basically is called as the idle capacity of that constraint. Okay, so that means what we can interpret here is the fact that we can in fact, we write it like this only, that the idle capacity of constraint 3 is 10 units. See, for me 10 is a number. Okay, I don't know what 10 is. 10 is hours, or 10 is number of manpower, or 10 is amount in liters or amount in tons or whatever. When I solve this problem, I am not taking units of measurements into consideration, because for me 10 is a number, right? So that is why what I am trying to tell the decision maker is that, because what I have observed from my solution, that the third slack variable has ended up as a basic variable with a positive value of 10. Okay, so basically what I'm trying to tell him is that there is a slackness, the capacity. See, basically left hand side of the constraints are telling you the utilization. So that means utilization basically means the capacity to which we are actually utilizing that resource, right? And the right hand side is the availability. So what it is trying to tell me is that my third constraint is actually sitting idle. Okay, it is not being utilized optimally. Had it been utilized optimally, even x6 would have turned out to be 0. And if x6 would have turned out to be 0, I would have definitely got x3 as my optimal basic variable. So in that case, the decision maker would have got a practical, ideal solution for his problem, where he would have manufactured all the 3 units that he was actually manufacturing, right? So X6 coming up as an optimal solution, as a basic variable in the optimal table with a positive value, means that the ideal capacity of my constraint number 3 is 10 unit. Okay. So in fact, the not just this. So basically, your slack variables in the basic solution, optimal basic solution, give you information about the idle capacity of that particular resource, right? This is one aspect. Okay. Now, if you just look the Zj minus Cj column of your primal table, right? Let's come to this. Yeah, here. If you just see the Zj minus Cj row of the final simplex table. Now read the Zj minus Cj's of slack variables here. यही थे ना हमारे पास. And they were the solution of the dual. Right? That's why we got y1 y by 3, y2 2 by 3, and y3 0. This is what we got, right? Now, if you observe, y3 number 1 was the dual variable corresponding to the third constraint of the primal. And because you have third slack variable in the basis, optimal basis of the primal, that is why you get y30. Had there been x3 here, even we would have got a positive value here. Why? Because what would have happened? If x3 becomes a basic variable in the final optimal table, this value would have been 0, right? Because then the basis here would have been 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, so what would have happened? This 14 by 3 would not have been there. It would have been 0. And what would have happened then? Because this would have been the optimal table with a finite unique solution. So only 3 zeros in your Zj minus Cj row of the optimal table. So definitely this would have been a non-zero value, right? So because you have x6 here as at a non-zero value, that's why the Zj minus Cj of x6 is 0. And that is why the dual variable corresponding to the third constraint is 0 as a solution of your dual. Is it clear? Am I making sense or not?
Yes, ma'am.
Right. So that is why what we do is, if the slack variables correspond for the idle capacities, the Zj minus Cj's of the slack variables, they correspond to what we call as the shadow prices. Now, what do we mean by shadow prices? I just come to that. They are actually the marginal values of the constraint resources. I'll just come to that. That means this actually tells us that how much they actually give you the amount of increase in the total profit, which can be achieved when one additional unit under that column is available. Okay, I'll just come to that. Okay, let's see. I'll write it as y1 only, because it's understood that y1 kitna tha hamara? 14 by 3, right? No, sorry, 5 by 3, right? And this was actually your Zj minus Cj of x4, right? Your y2 was 2 by 3, which was zj minus cj of x5, and your y3 was 0, which was actually your zj minus cj of x6. Okay. So when I say that this value, let's interpret this. Okay. Now, y1 turning out to be 5 by 3. Now, y1 corresponds to what? x4, right? x4 corresponds to what? The slack variable of the first constraint, right? Now, your first constraint corresponds to what? Wood, right? Basically, this amounts to saying that if I remove 1 unit, like, and the availability of wood to me is 90 units. Okay. So if this amounts to actually saying that if I'm repeating it again, if you want to write it somewhere, you can write it. If one productive unit of the first constraint, of the first resource, is removed from the right hand side, that means if the decision maker decides to remove 1 unit from the wood, he says, I want to compromise, I want to reduce my costs, okay, let me order less wood. Okay, so then I'm going to tell him that if you remove 1 productive unit from the right hand side of this constraint, then the total contribution to your profit is going to be reduced by 5 by 3 units. Okay, that's why we are calling them as shadow prices. Okay, they are related to the prices, but behind the scenes. Okay, so that is why the zj minus cjs of the slack variables are actually also called as the shadow prices. So see, just look at the beauty of this simplex algorithm. You are not solving the dual. You have just solved the primal, and you are actually getting all the information related to cost, related to profit, related to changes in your inventory, and you are able to tell the decision maker everything that he wants to know. So that is why I said strong duality theorem was a major breakthrough for economists. So they could interpret everything, right? So basically, this is how we interpret, the solutions. But if you just look at this, you're saying y3 is 0, right? But this corresponds to x6. So how do we do? That means basically if we remove this quantity, the third constraint, that was with regard to polish. Okay. Now, he says, okay, if I read it this way, then this amounts to saying that by removing 1 unit of polish is not going to change my contribution in the objective function to my profit. Okay, but then he's going to ask till what extent? ये तो मैं polish remove करता जाता हूँ, right? But no, that is not the case, because we have got the idle capacity of constraint 3 to be 10 units. So we end up concluding that you can reduce the right hand side of this third constraint up to an idle capacity, okay, up to its idle capacity, and there won't be any change in your objective function. But if you try to remove it beyond the objective function, beyond the idle capacity, then this value will change. Okay, so if he wants to reduce on the cost, then he can do so by ordering less polish, but till what extent? Only up till 10 units. His profit, his value of the objective function is not going to change till this range is attained. Okay, so this is how we interpret the primal and the dual solutions from one table itself. I did not write the optimal table of the dual, remember, and I could interpret everything with regard to the profit, with regard to the cost, with regard to his, I was able to give him suggestions that he can, if he wishes, he can reduce the inventory of his polish constraint, but only to a certain extent, not forever. Okay, so I mean, this is all that we normally talk in duality, and this actually finishes off your duality as well. Okay, so